Okay, so we want to look at capacitors in series and parallel. Alright, and we'll start with the parallel case first. So this is just to reiterate some of the things we've done in class. And let's say if we have a circuit here, I have two capacitors, and I hook them up with wires as such. Alright, so we'll call this capacitor C1, this capacitor will be C2, and our battery is going to have a voltage V. Now recall that C equals Q over V. So the voltage between C2 is going to be V, and the voltage between C1 is also going to be V. So the V's are going to stay constant in this case. So using the definition, we can write C1 is equal to Q1 over V, and C2 is equal to Q2 over V, where Q1 and Q2 are the total charges on the capacitors. Right? And we want to know what is the equivalent capacitance. Right? What is the equivalent capacitance here? Alright, so let's think about that real quick. Well, first of all, the total amount of charge on C2 here, again, will be Q2, and the total amount of charge on C1 will be Q1. So if I draw an equivalent circuit here, then I'm going to have a capacitance with C equivalent, and the total charge on this guy will be Q total, where Q total is the sum of Q1 plus Q2. Right? So let's go back and solve these equations for Q1 and 2, and then we'll add them up. So remember that Q1, if we solve the equation, Q1 is going to equal C1V, and Q2 is going to equal C2V, and that means that Q total is going to equal C equivalent times V, and again, the voltage across here is going to be the total voltage of the battery V. So that gives us C1V plus C2V equals C equivalent times V, and now my V's cancel out, and C1 plus C2 is going to equal my C equivalent. So in parallel, capacitors add. Okay, so now let's look at the series case, and we'll just have two capacitors again. And we'll call this one C1 and this one C2. Now remember that as the current flows out of the battery onto this plate will get a charge of negative Q. I'm sorry, it'll get a charge of positive Q on it if this is the positive terminal, that's the negative terminal, and that means that this guy will have a charge of negative Q deposited on him, and so this capacitor will have a total of Q, and this capacitor will have a total of Q. So the Q's are going to be the same in this case. But what's different is that this will also have V1 and V2, and in this case V1 plus V2 must equal V. Alright, so that's the key here. So remember, going back to the definition of capacitance, if I solve this equation for V, then I'm going to get V is equal to Q over C. And if we go back, then we can see that if I want to draw an equivalent circuit here, that the equivalent circuit will look like this. And this one capacitor will have a charge of Q, and he will have a total voltage drop of V across him, right? And his capacitance will be C equivalent, but we want to figure out how to calculate that C equivalent. But the way we do that is go back to this equation. All right. So once again, recalling that C1 equals Q over V1, and C2 will equal Q over V2, and we have that V1 plus V2 must equal C equivalent. Whoops, that's V equivalent. Sorry. That will be V equivalent. So then V equivalent will just equal V1 plus V2, and V equivalent, if we go back, is equal to Q over C equivalent. So that means that V1 is equal to Q over C1, and V2 is equal to Q over C2. And again, we have the nice cancellation, and we get the final result that 1 over C equivalent is equal to 1 over C1 plus 1 over C2. Now, quick trick to solve this problem, right? We can multiply both top and bottom by the other denominator, and that'll give us C2 plus C1 over C1 times C2, and when we take the reciprocal, it's just going to be the product of the two over the, not a resistor, but a capacitor, over the sum of the two. So we'll have C1 plus C2. All right? And if we have more than one, so let's, or I'm sorry, more than two. So let's say we have the case where we have 3 capacitors, or so I have 3 capacitors in this circuit, and they're labeled C1, C2, and C3, right? Then we're going to get that 1 over C equivalent is equal to 1 over C1 plus 1 over C2 plus 1 over C3, and this can get pretty tedious, but a quick shortcut is to multiply by the other two denominators to get or common denominators. So if I multiply 1 over C1 by C2 C3 over C2 C3, then I get C2 C3 over C1 C2 C3. If I do the same thing for 1 over C2, I get C1 C3 divided by C1 C2 C3. And if I do the last one, I get C1 C2 over C1 C2 and C3. Right? So now we have our common denominators, and our equivalent resistance in that case will just be the product of all three divided by the sum of each individual combination of any two resistors. C1 C2 plus C1 C3 plus C2 C3. And that formula will hold for any combination of 3 resistors. If we had 4, then it would be C1 C2 C3 times C4 over C1 C2 C3 plus C1 C2 C4 plus so on and so forth, right? So that's a general formula. Now, in our case, let's move to the homework, right, where we do have more than more than two capacitors. So quick hint on this problem. Let's look at how we might use that information to solve this problem. And so what we have is a battery of 9 volts, and this is 8 microfarads, and this is 6, this is 2, and this is 8. Right? Now, using the rules we just discussed, okay, when they're in parallel, these are just going to add. So our equivalent, if we add those two, our equivalent circuit will look something like this. And this is just going to be 8, 8, and 8. And so our equivalent resistance, let's start with the 1 over case. It's going to be 1 over 8 plus 1 over 8 plus 1 over 8. And that equals 3/8. And so the equivalent resistance, or capacitance, I'm sorry, is going to be 8/3 of a microfarad. Alright, so just a little bit over 2 microfarads. So that is how you get the reduced circuit. Right? Now, recall to solve part, well, I guess we did just solve part A, didn't we? But to solve part B, the charge on each capacitor, label this as C1, label that as C2, and label that as C3. Alright, label that as C1, C2, and C3. And if this is your total voltage, then V1 plus V2 plus V3 must be the voltage drops across each. So that'll give you V1 plus V2 plus V3 is equal to V total. And then you can rearrange this equation as we did before using the definition of capacitance. Well, that needs to be Q over V. Right? And because you know the capacitance, you should be able to guess at the value of V across each one without doing any more work. But another hint, if you're not seeing what the voltage drop across each one should be, go ahead and then make one more reduced circuit here, and you'll have this. And because you have this, you know what V is. It's 9 volts. You know what your capacitance is. You know what, you can figure out what the charge across the capacitor must be. But because this is a series combination, each capacitor must have charge Q on it from this calculation. Okay? And then from there you can apply C1 equals Q over V1 to solve for V, and so then V1 will equal Q over C1, and V2 will equal Q over C2, and so on. Alright, so that gets you started on that one. I don't know that I need to do anything from problem 2, so unless there are any emails that I get, I don't think we'll do anything with that. I will say a word about problem number 3, and that is this. So here's our battery, and I've kind of drawn this backwards, but it really does not matter. Alright, the direction that your battery is going doesn't matter. So we have a nice resistor here, and then we have a resistor here, and we have the 2 up here. So we have this circuit. Now, I'm not going to put in the numbers, I'm just going to call this R1, R2, R3, and R4. Alright, so to reduce this into an equivalent resistance, right, the whole point of part A is to find the equivalent resistance. Note that these two guys are in series, and so if we have an equivalent resistor for those two guys, then our picture will look something like this. And this will be R2, 3. And again, that'll be R3 and 4, won't it? Yeah, that'll be R3, 4. And this is R2 and R1. And now these guys will be in parallel with each other. And then that combination will be in series with R1. So that gets you started there, and then you can work backward. All right, you can work backward to then find the current delivered through each resistor. Now, remember that the current through R1 will be the total current. And then for part B, part C, we want to determine the power delivered by the battery. And to do that, remember that P is just equal to IV, where I is the total current and V is the voltage across the battery. And then D, we want to find the power delivered to R4, right? So your whole goal is to use Ohm's law. Once you find the equivalent resistance, that'll give you your total current here. And then that total current will branch off into two different currents, one in that direction and one in that direction. And we can call this I2, and we can call this one I3, and I total must equal that sum. Right? And how can you get I2? Well, if you know what the voltage is, which of course the voltage across this branch is going to be the same as the battery, or will it? Ooh, be very careful, there is a resistor there. Alright, there is a resistor there. So your job is to determine the voltage drop across. Let me draw one more circuit here, the equivalent circuit. And once you have added your parallel branch in series in parallel with the other guy, then you have this guy, which is R2, 3, 4. And you have R1 here, and using Ohm's law, once you find the total equivalent resistance, you can find the total current, and that must be, you can then apply Ohm's law, V equals IR, to find the voltage drop across this guy using the values of I and R, and the voltage drop across this guy using the values of I and R. Right, so you'll have voltage drop 1 across here and voltage drop 2 across here, and that will be the same voltage drop as across this entire branch. Okay, that'll be the same voltage drop as across that entire branch. And so then you can kind of work backwards a little bit and apply Ohm's law as necessary to get the current through each resistor. And then once you have the current through each resistor, you know the voltage across each resistor, you can then calculate the power. Alright? Okay. Alright, now number 4 is probably the most difficult one on here. Alright? So let's draw this just real quick, and I'll give you a few hints, and we'll see what we have as a result. Alright, so we have something like this, and we're given that I1 is moving this way, and then I2 branches off this way, and I3 moves this way. And we're given that this is a 24 volt battery. Whoop. And this is a 12 volt battery. And so we want to know what the total currents here are. Now I'm not worried about the resistors, alright? Again, we'll just label these R1, R2, R3, R4, and R5. And now the whole point, right, is to apply Kirchhoff's rules. Not Kirchhoff, Kirchhoff's rules. And so we need 3 equations since we have 3 currents, but you already have one of them, right? And that is because you see the current coming out this way and through this way, that must be I1. It branches out right here and then goes that way and then that way. And then they must add back up here and go back into this battery. And so you already have your first relationship that I1 equals I2 plus I3. There's your first relationship. And now the question is, how many loops are in this circuit, right? How many loops are in this circuit? And the answer is there are 3 of them, right? So we have one loop right here, and we have a second loop right here, and then we have the loop all of the way around the circuit here. So we have 3 loops we can choose from. It might just be easiest to use the red loop and the green loop, right? And if we use the red loop and the green loop here, then what we can do is let's start at the battery, and as we go in the direction of R1, we'll traverse the 24 volt guy. So we'll have 24 volts is equal to minus I1R1 minus I1R2 and then minus I3R3. Okay, so we will have 24 minus R1 I1 minus R2 I1 minus R3 I3, right? And that must all add up to 0 since we went all the way around the loop. And then if we go around the green loop here, we'll have 12 volts. If we start right here, we'll go 12 volts, and we'll go plus R3I3 minus R4I2 minus R5I2. So we have 12 volts plus R3I3 minus R4I2 minus R5I2. Again, all of that equals 0. All right, so there's your three equations. Label those 1, 2, and 3. And I don't care how you solve these, okay? I don't care how you solve. And, I mean, you can use matrices, the methods from class, or a computer program. I just do not care how you solve these. Just get a solution, okay? Just get a solution. Alright, so now let's move on to number 5. And here we have a battery, and we have a capacitor, we have a switch, and we have a resistor. Alright, and we have this configuration here. And they label it E, and again, for our purposes, E and V are the exact same thing. Alright, and what we want to know is the time constant, part A. We want to know the time constant. And the time constant is denoted as tau. And remember that that is just the quantity RC. Okay, that is just the quantity RC. And part B, we want the maximum charge on the capacitor after the switch is closed. After the switch is closed. Alright. Well, how can we get that? Well, after the switch is closed, right, after the connection is made and the switch is closed, then we have just a normal circuit, and, well, what's going to happen here? What's going to happen to C? Well, we're going to have current coming out of the battery this way and depositing charge on this plate of the capacitor. That will drive the opposite charge off this way and complete the circuit, and current will flow. And eventually this capacitor, the capacitor will have all of V across it. And if the capacitor has all of V across it, how much charge will that be? Well, you can find that from C equals Q over V. Solve that for Q. Right? And part C is going to be a little bit trickier. Right? Part C is a little bit trickier. We want to find the current after 10 seconds. Well, here's the hint. So remember that current is equal to Q, technically delta Q over delta T. And here, for an RC circuit, Q, the amount of charge on the circuit, or in other words, the amount of charge that is flowing through the circuit at any given time, is equal to Q times 1 minus E to the negative T over RC. Okay, now, but remember that for a resistor, okay, the current flowing through the resistor is going to be the same as the current flowing throughout the entire circuit, right? And let's see why. So the current flowing through the resistor here must be the same current flowing out here. Now, of course, that current will drop. Okay, that current will in fact drop. Okay, but how can we use that fact? Right, so this represents the amount of charge accumulating on the capacitor, not the charge that's necessarily flowing through the circuit. Okay, I want to make that distinction very clear. But what we can do, right, is use our equation Q equals Q times 1 minus e to the negative t over RC, and look at the voltage across the capacitor at 10 seconds. So to find the answer to this question, find the voltage across the capacitor at 10 seconds. So plug in for T. In for T, and you'll get Q equals big Q times 1 minus e to the negative 10 over RC, whatever RC, R, and C are. So you'll calculate this value of Q. Then you can use the fact that the voltage across the capacitor is going to equal the charge on the capacitor divided by its capacitance. You can find Q, the voltage, rather. Right? So you can find the voltage, and then the voltage across the capacitor. So let's look here. You have some voltage across the capacitor and some voltage across the resistor. So this is your total voltage. You have some voltage across the capacitor, some voltage across the resistor, and your voltage across your resistor must equal your total voltage minus the voltage across the capacitor. So if you can find VC, you can calculate VR. Now that you know what the voltage across the resistor is, you know its resistance, so I will equal VR over R. Alright, so there you go.